Alright. Before we start, as usual, I will recommend you to watch these videos first. If you're done, let's get into it. Remember that until this video, we get 4 elegant equations that explain electric and magnetic field and the relation between both. Here, in Faraday-Lenz induction law, we see that if we take divergence to the equation, of course, by vector calculus, it equals to 0 for left-hand side, and for the right-hand side, if we took the divergence to, we will get as this is equals to 0, but here, there is a problem. If we take divergence to the Ampere law, the left-hand side is equals to 0, but for the right-hand side, is the divergence of charge here necessary 0? Here, if we remember about this equation or continuity equation, then if we assume that our charged particle system not going anywhere or charge is conserved, then this part is about this and the row here related to this. Here, we know that charge is conserved, but there is something missed in our equation. So to fix Ampere law here, we first assume that we can add some term, let's say with J capital I factor here, which in this new equation, J capital known as electric current density because of moving charge, but here with index I is about the other. But what is it? Let's check in this illustration. Suppose that we have this two-plate system connected with wire that the right here positively charged and the left here negatively charged, or known as capacitor, that here if we have this loop system with a battery here, of course this is positive and this is negative, so the magnetic field in this system will create as this, which edge effect is negligible. Here we know that inside the capacitor here, J capital is equals to 0, but in our loop here, the J capital isn't 0 vector. If we have alternating current or current depend on time here, then the electric field here is time dependent. But here, even if time dependent, the J capital is still 0, but the circuit still works. So here, we need to fix as J capital I factor here proportional to first partial derivative for electric field with respect to time. So here, by this proportionality, it may satisfy charge conservation, of course, and the second, for capacitor in all conditions, the circuit still works. So here, to make the charge conservation, we make this equality J capital I factor is equals to epsilon 0 and first derivative of electric field with respect to time. And then after substitution, let's check this equation. In the left hand side, of course, is equals to 0 by vector calculus identity, and the right hand side we took divergence for each term, and the second term here is related to Gauss law that relate to charge density, and then we get this equation for charge conservation, which is the derivative of Q with respect to time is equals to 0, then this equation leads to 0 as charge conservation. Here, our new equation again satisfy continuity equation and work for all capacitor condition. So here, our 4 equations about electric and magnetic field universal for at least classical electromagnetism. These 4 equations popular as Maxwell's equations that being fundamental to Maxwell electrodynamics theory. And some footnote here, if we take the curl of the Faraday-Lenz induction law, we will get this equation, which here we get from vector calculus identity, and for the right hand side, if we take curl here, by combination with the Maxwell's equations, we will get as this, and so on if we take the curl for Ampere-Maxwell law here. If we at least take these 3 or the curl of J and linear combination of gradient of charge density and the first derivative with respect to time for the J capital factor here, then we will get these 2 equations will become as this, which here Laplacian minus this second derivative with respect to time operator known as the D'Alembert operator, as we know in field video about wave equation, which here in previous two equations is about wave equation with source, and these two result is about sourceless wave equations. And another footnote here, if we define both electric and magnetic field as potentials, then we will get by the Maxwell's equations as this, which here if we take divergence of A is equals to 0, then we will have this is 0 and this is 0, but here is non-zero. So our potentials equation will become complicated. So how to fix it? Besides using only divergence of A, here we choose that this equation is true, which here we're adding scalar potential phi. If this condition true, then here is equals to this and this nabla dot A, and then this first derivative of scalar potential phi is combined as 0. So then the potentials equation will become as this. Such a beautiful wave equations with source for potentials. Here, the divergence of A is equals to 0, which we not use in this formulation known as Coulomb gauge, and the other here which we use is about Lorentz gauge. And here, the source of this equation relate to Maxwell equation source, but with more simple and beautiful solutions. Here about something we call gauge will be our discussion in future videos. And that's the completion for standard Maxwell's equations in Maxwell's electrodynamic theory. I hope you enjoy this video. If you like this video, don't forget to share and subscribe. If you have any questions, drop the comment below. And that's it. See you later.